So this one here is a little bit irritating to do, so I'm going to be doing it on without my beautiful face in the picture, just so that way you have a little more space to actually look at the problem. So let's get started on this. So when I'm looking at this, it's automatically going to be an irritating problem because we have this table over here. Super easy to screw up this table. Basically, what you're going to be doing here is instead of actually having things to derive and integrate, you're going to have to use this, take the derivative. So for example, if I give you f of 3, if I want to take the derivative of f of x at 3, you're going to have to go f prime of x and then input your 3 over here. So you got to make sure you're plugging in the right thing. And normally there's like composite functions and you have to use chain rule, product rule. So if I have f of x times by g of x and I'm taking the derivative and evaluating at x equals 2, we're going to have f of x times by g prime of x plus so on and so forth. And then so you're going to have to do it like that and then back up. So it says here, explain why there must be a value for r such that h of r is equal to -5. Now the second I see this, something I want to bring up, there's a difference. And there are these two formulas, or these two theorems that we haven't touched in a long time. The first is IVT, and this stands for intermediate value theorem, and that's the one where it says if I have two numbers like 5 and 10, if I have a number where one's 5 and the other one's 10, that means somewhere along the line I have to cross every single number. If it's continuous, I can't just jump from 5 to 10. So if I said, is there any t where f of t equals like 8, according to IVT, there would need to be one, because let's say f of t starts at 5, it ends at 10. That means in order to get from 5 to 10, I have to cross over 8 somewhere. So that's the basic idea behind IVT. And anytime you're saying explain why there must be a value, you're using IVT. So let's be using IVT really quickly. So what that means is we're going to find what is h of r. Sorry, let me pause real quick and adjust my mic. All right, I had to get that out of the way so I just wouldn't keep hitting it. So basically what we're going to do is we're going to say what is h of 1 and what is h of 3. And I guarantee you these are going to be straddling -5, meaning one's bigger than -5 and one is smaller than -5. So in order to figure this out, what we know is h of x equals f of g of x minus 6. So in order to find h of 1, in this case, let's zoom in a little bit. This is going to be equal to f of g of 1 minus 6. Now I always erase it I always write it out because this is so easy for me to screw up personally. But if you want to kind of like keep track of it, you guys can. But again, that's a really easy way to make mistakes. I always like to write it out. I'm going to be erasing it as I go, just purely to save space, because I believe since it's a 4-parter, I might need every single inch of this paper. So we have h of 1 is f of g of 1. So g of 1 is going to be 2. So we're going to replace this g of 1 with a 2. Again, I'm erasing it. You guys can just rewrite it if you want. And then finally, we're going to take f of 2. And in this case, f of 2 is 9. So that means this is going to be 9 minus 6, which in this case is going to be 3. Which means that most likely my h of 3 is going to be less than -5. So something like -10 or something like that. So it's going to be equal to f of g of 3 minus 6. So g of 3 in this case is going to be equal to 4. And then that means I need to find f of 4, and f of 4 is -1 minus 6. So yeah, this is equal to -7. So we can say, yeah, that must be true. So for A, we know that there is some h of r where h of r equals -5 due to IVT. And basically what you're doing is you're showing one's bigger, one's smaller. You don't need to explain it. You can just say it and leave it like this. However, you do need to show one number's bigger, one number smaller. Then you can say, yeah, there has to be -5 due to IVT. It's going to have to cross over -5 to get from 3 all the way down to -7 because it is continuous. It was given that it's continuous. One thing you're going to want to do as well is you are going to want to say that we know that it is going to be continuous as well. So you might want to write that out. Okay, next for B. It's going to say, why is there a value? So again, we're going to want to use IVT, but the problem is we're not dealing with values anymore. We're dealing with slopes. Now, you could technically try out IVT and see if it works, like what is h prime of 1, h prime of 3. That might work, but generally, whenever you see slopes, you're going to think of MVT, and that stands for mean value theorem. And what mean value theorem says is if I have any sort of curve, if I take my secant line at my endpoints, there's some slope, instantaneous slope or slope of a tangent line where these two are equal. And again, this is just normally. So you can always try IVT here. So you can find what is h prime of 1, what is h prime of 3, try that out. But normally if you see derivatives, you're going to be dealing with MVT. And basically what you're going to be doing is you're going to take the average rate of change. So you're going to take h of 3 minus h of 1 over 3 minus 1. Again, this is your secant line slope, your average rate of change. And then you're going to say this has to be equal to -5 somewhere. And then you're going to find it, and it's probably going to be -5. And then in which case you can use MVT, which says that your instantaneous rate of change must equal your average rate of change somewhere, or your mean rate of change, basically. So let's figure it out. H of 3. So we knew that h of 3 was equal to -7 minus h of 1 was 3, all over 3 minus 1. So we're going to have -10 over 2, which is my -5. And then you can say due to MVT, there is some C. Again, this is one of those where we don't really use mean value theorem too much. It does come into play a couple times, but this is pretty much majorly where it's going to show up, where you're going to say, hey, how do you know that I have to have some h of r equals -5? How do you know there has to be some f prime of x that's -12 or something like that? And whenever you're saying that explanation, how you know that there has to be a value that matches that, that's normally IVT or MVT. Again, IVT is normally saying I straddle it, so that's if you're dealing with h of x, h of t, f of x, f of t, something like that. And then MVT is normally when you're doing h primes, because you're saying the secant line slope is the same as your instantaneous rate of change somewhere along the line. Okay, next we have our let w be a function, find the value of v prime of, or w prime of 3. Okay, so basically what we have here is we have w of x equals integral from 1 to g of x f of t dt. Find w prime of 3. Now, basically what we're going to do here is I'm going to use FTC, Fundamental Theorem of Calculus. So then I'm going to say w of x equals f of g of x minus f of 1. Excuse me, capital F. The integrated version. And then if I want to find w prime of 3, what that means is I'm going to have w prime of 3 equals f of g of 3. Notice it's lowercase because I'm doing chain rule. I'm taking the derivative of this f and evaluating at 3 times by g prime of 3 minus 0. Now the reason this f of 1 becomes 0 is because in your original w of x function, I was doing f of 1, which means that this is going to be a constant. So when I'm taking the derivative of a constant, it becomes 0. So if I wanted to do this a little slower, I could go x, g of x, g of x. So again, this is chain rule. So I'm taking the derivative of your capital F function, which gives you your original F function, and then I'm leaving whatever's on the inside. Then I have to take the derivative of the inside due to chain rule, which gives me g prime of x. Now from here, I'm evaluating at 3. So we're going to say f of g of 3. So then g of 3 again was 4. and then let me rewrite this as 3. And then f of 4 was negative 1. So we have negative 1 times by g prime of x. And then that's going to be evaluated at 3. So g prime of 3 is going to be equal to 2. So w prime of x equals, or excuse me, w prime of 3 equals negative 2. I'm going to shrink this down a little bit. This didn't need as much space as it took. But yeah, this is basically the whole idea. This is fundamental theorem of calculus. Again, the reason why I know that it's fundamental theorem of calculus is I'm taking the integral with this like weird thing up here, and I'm like, well, if I and I don't know what my function is, but I do know how to evaluate my functions over here. So whenever you're like, I don't know what my function is, but I know what the evaluated version of certain things are, you can always try that out over there. Okay. Again, fundamental theorem of calculus is integrate, plug in the top number, minus integrate, plug in the bottom number. All right, so finish 3 parts. Let's work on our last one. All right, I guarantee that there is a really amazing way to do this problem. I do not have one though. What I'm going to do here is understand what the inverse of a function is. And the main idea with an inverse of a function is you're swapping around your x and y. So for your slope, so g prime of x is going to be equal to, whatever g prime of x is, this is the slope of your g function. But if I take g inverted and I take the prime of that, this is going to be 1 over g prime of x. Because basically you're swapping your rise and run, right? You're exchanging all your x's for y's. So where g of x is your original rise over run, g inverted prime is now run over rise, which is why we have that 1 over kind of deal. It's not a negative 1. Remember, it's not a negative 1. It's an inverse symbol as well. So we can't just use our power rules here. Also, anytime I'm evaluating, you got to be careful, because if I were to say something like g inverted of like 2 or something, I'm not going to look here and look at g. I'm going to look where's g2 and then go backwards to get my y. So it's really, really freaking irritating. But again, as long as you're kind of understanding inverses, it's really, really not too bad. So g is the inverse, write the equation of line tangent at x equals 2. Well, that's convenient. So then here's what you're going to need to do. Here's what you're going to need to write your line. You need g inverse of 2. And then secondly, you need g inverse prime of 2. All right, let's get going here. So then what we're going to do first is we're going to find my point. So g inverse of 2. So where x was 2, or where y was 2, now x is 1. So my point that I'm going to be using, is 1, 2. And again, because we're swapping our x and our y. Oh, excuse me, and then now we have to swap it, so it's 2, 1. So again, I'm looking at my g function. For my g function, I got 1, 2, and for my g prime function, or g inverse function, I got 2, 1. And then now from here, we're going to have to take our derivative. So whatever my g function was, g inverse prime is going to be equal to 1 over g prime of x. And again, all of your rises and runs are swapping. So I misspoke earlier, I think. I said you're supposed to take g inverse of 2, but basically that's going to be inverse of 1. It feels a little funky to say it like this, but basically what's happening is, again, if you plug in your y function, it's the same as swapping your rise and run. So you always have to swap your x's and your y's. Again, this is just an inverse function thing. If you guys are really good at inverse functions, this is not too bad. But again, it's just taking what you know and adding a convoluted inverse function portion to it. And I hate it. It's great. So then from here, my slope in this case is going to be 1 over g prime of 1. And so g prime of 1 is 5. So in this case, my slope is 1 over 5. Okay, so then this is my slope. This is my point. So when we put it together, I get y minus 1 equals 1 over 5 parentheses x minus 2. And then this is the equation of the tangent line to my g inverted function. Again, they take such a simple concept like writing a slope of a tangent line and make it irritating because you got to think backwards due to the fact that you're dealing with inverses. Again, least favorite problem. Such an easy topic, but they just make it so irritating because MVT, IVT haven't done that in a while. And also fundamental theorem of calculus, super easy to like skip over because we're like, we want to find the derivative and integrals of these. But whenever you see that you have some sort of like variable or something in your integrand and stuff, you always kind of want to set up and be like, oh, I probably am going to use fundamental theorem of calculus. Okay. Biggest topic here though is whenever you see this table over here, you almost never, you don't care about the function. What I mean by the function doesn't matter is you're never going to know what f of x actually is. You really are just saying, okay, how do I play with it? Which is why fundamental theorem of calculus is so nice, because instead of having to actually integrate a function, you can write it as like f of 2 minus f of 0 or something like that, right? That's why it's so nice. Okay, this one probably going to get a lot of questions. I feel like I didn't explain the inverse one too great. But again, if you have questions, let me know. It's literally the same thing. You need a point, you need a slope, but because they're inverted, you're swapping back and forth between, am I looking at the x or am I looking at the y? Whenever you're looking at your original function, you're looking at the x. Whenever you're looking at your inverted function, your x's now become y's and vice versa. Okay, that's 3, halfway there.